So welcome everyone to the 20th session of Statistical Learning in Practice. We're going to begin with just time series, very briefly what a time series is, and then we'll focus on stationary time series, and that's going to be the focus of our sessions, because we don't really have a lot of time to talk about time series. So we'll just focus on some sort of textbook examples of them. Okay, so 3 time series. So as I was just saying, a time series is a collection. So a time series. Okay. So a time series is a collection of random variables indexed by time. Okay, or mathematically, what we have is that X is this collection that is indexed by this T time set. Okay. So of course, X is fully determined by the joined distribution of xt for t in this capital T. And we could model this, but this is going to be too ambitious. Yeah. So modeling and estimating this in is generally too ambitious. Yeah? And why is that? Well, in practice, we only observe one instance of x1 to xn, say. Okay, so so we only have a section of one path, right? So that just doesn't sound like a lot to be making statistical conclusions from. And this is where, the view of having some sort of regression structure makes sense, because, then we would be seeing repeated samples from a random variable, but maybe with some dependencies between them, and that we need to estimate as well. Okay, so we need models in which, having this single path is enough to be making inference. And again, if they were independent, then we could be following a regression setting. And so we know that there exists such models. So now we just need to propose some which are acceptable from this point of view, right? Okay, so we need assumptions. So let's then now talk about stationary time series. So that's 3.1. Stationary time series. And let me begin with a definition. So definition 19. So X, and X will now be just any time series throughout. So X is strictly stationary and I will shorten this as S. If we have that the joint distribution of xt1 to xtk equals the joint distribution of xt1 plus h up to xtk plus h. This is for all t1 to tk and h in our set, in our time set, and for all k natural numbers. Okay. So again, so before I say that, so what are the consequences of this definition? So note that if x is strictly stationary, then the distribution of these random variables is actually constant in time, right? That's the first thing. And then the other thing I'm interested in is a second moment, to understand what it means in terms of second moments. And this is in some way related to regression again, yeah? Because we, at first we're interested in first and second moment assumptions. Well, this would completely pin down the first and second moment of a single element of the time series. But because it's a time series, we also need to know dependencies. So, at first we're interested in the first order, so to say, dependency properties of such time series. So let me introduce then a couple of objects. So if the variance of xt is less than infinity for all t, then we define the following quantities. So define gamma x as t, which is going to be the covariance between xs and xt, okay? And this we call the autocovariance function, which we will refer to as ACVF. And then rho x as t will be the correlation between these two, which is no more than, of course, the gamma x as t divided by square root of gamma x as s gamma x tt, right? And this is the autocorrelation function, or ACF. Okay, so having this, so this is in some sense the bare minimum dependency quantity that we can be looking at, right? Because this is linear dependencies, so that's the absolute most basic dependency that we can think of. And so what is it for strictly stationary time series? Well, what we have here, so then let's say, so note again that if x is strictly stationary, then what we have is the gamma x as t equals gamma x s plus h t plus h for all s t here and h here, right? And actually we could have even h to be in the I mean, we're thinking, by the way, all the time of capital T, and maybe I should have written this. Yeah, so capital T, so this time set, so let me just write here above. So T will be the natural numbers or the integers for us, generally speaking, but actually we will take the integer, the integers here. So we could have just taken S, T, and H in the integers. Yeah. Okay, now, having such, having that the joint distribution is invariant to shifts is a bit too much. Yeah. So strict stationarity is too strong. And on top of that, it's hard to check in practice. Yeah. Because you only get this sort of finite window of observations, right? Hard to check in practice. But we maybe retain first two moment properties, yeah, first two order properties. Okay, so this gives rise to weak stationarity. So definition 20. So we say that X is stationary or weakly stationary or second order stationary. So I write it in brackets because you can simply say stationary and that will be second order. If the expectation of xt equals mu for all t in your set, so therefore we have that this is constant. Then second, the variance of xt is finite for all t in this capital T. And then last, we're going to assume that the autocovariance function only depends on the absolute value of h, where h is s minus t is the lag, so-called lag. Okay, and we will write, so generally we'll write gamma x of some positive number to denote this gamma x as t when the difference between them is h. Yeah. So we sort of redefine the gamma x to not be, of two arguments, but rather just one, which is a natural number, maybe including 0, and because that's going to be, because whenever you plug in here, say 5, then that will apply to any st that have difference between them of 5, then we'll be fine, yeah, with this quantity, looking at that quantity directly, because we're going to focus on weekly stationary time series. Okay, so you could check as well, check that strong stationarity plus finite variance implies weak stationarity, yeah, or just stationarity. Okay, now an example of a weakly stationary time series, which is a key example, is white noise. So white noise is this W, have T and T, and we're going to have, we're going to denote this guy as Wn for white noise, 0 and sigma squared, if the expectation of this guy is 0 for all t, then the variance of wt is sigma squared, and this guy belongs to 0 infinity, so you cannot have anything that is infinite or 0. And last, we have that the covariance of this w, st, is 0 for all s distinct from t, and in all of this, s and t belong to our t. Okay. So we have that, we have uncorrelated random variables that have the same variance, and this is a finite and positive variance, and they have mean 0. Okay, so this is only talking about first and second order properties of this w. Okay. Okay, so now we need, we need something a bit more complex than this, right? as a stationary time series. And we're going to take, by the way, for now, so from now on, take t to be the integers, and let's also take throughout the mean to be 0, yeah, of any time series. And if it's not, then you simply just subtract the mean and you're done. Yeah? So you center the process. Just imagine that all of the processes we're going to talk about have been centered. Yeah. Okay. So let's motivate the processes that we're going to be looking at, which are RMAP processes. So these are autoregressive moving average processes, and they look very simple, but and they are so. And so you could be thinking, well, why would we go so simple? And so here is the answer to that, because actually they turn out to be fundamental in many ways, even though they are that simple. So let me just introduce a couple of, a definition and a result, and this will make sense. So definition 21. So X is a linear time series if there exists a collection of real numbers, sequence of numbers, satisfying that they are absolutely summable. Okay, and this is therefore here. And also white noise such that X can be written as the sum of the white noise weighted by these guys. Yeah. Okay, well, T is the as I was just saying, we've taken T to be the integers. Okay, so we can write X as this transformation of the white noise, then we say that X is linear. Okay, and this type of transformation is actually a very common thing. So this is called filtering. Okay, so we filtered the white noise, and let me talk about filtering in general. So proposition 2. So let Y be stationary and for sequence like before, let xt be again the sum Okay. So this really is filtering the white process. Okay. So if we filter the white process and we put the following condition, so we say that these guys are absolutely summable, then x is stationary. Okay, so we can create a stationary time series by filtering it. Okay, and remember, I mean, the white noise is a time series. Sorry, it's a stationary time series. So therefore, this means that a linear time series is stationary. Okay, so a linear is stationary by definition. Okay. So now that we've seen, an example of a stationary time series, this linear time series, well, let's see if this is any important actually, right? Because we have things that are non-linear and such things in mathematics, so maybe linear is just too narrow. But there is something called Wald's decomposition that I will not go into details of. So this is a very informal remark. So you don't need to know the decomposition itself, which says, roughly that any stationary time series is linear up to some deterministic process. Okay, I don't want to go into details of what a deterministic process is, but as you can imagine, it is, not as complex as the random part of any stationary time series, right? Okay, so what this says is that basically we can focus on linear time series because these are really going to have all of the meat of stationary time series. Okay, so. And within this linear time series, we have ARMA processes. So ARMA, these are the ones that are going to be of our interest here. So ARMA processes are the textbook example of linear time series. So I'm using processes and time series interchangeably, okay, of linear time series. And indeed, so it's not only that they are quite simple and so on, although, it doesn't make sense, the remark I'm making about them being simple because you haven't seen them yet, but I can tell you that they're not very complicated, so we'll see them at the end of the lecture. They do have a property that is fundamental, and it's the following. So for all autocovariance function gamma and h in the natural numbers, there exists an x being ARMA such that the autocovariance function of the x equals this autocovariance function that we've taken, just any, for all h going from 0 to this capital H. So we can replicate, or we can model any autocovariance function up to any value via ARMA processes. So they are just basically very fundamental. And they are a special case of linear time series, which are, as we've seen, the heart of stationary time series. Okay, so let's begin now with ARMA processes. So ARMA processes can be split into, or submodels are AR model processes and MA processes. Okay, so AR is autoregressive models, MA is moving average, and then we'll put them together to create ARMA. But before that, let's go separately. So then 3, 1, 1. So we have autoregressive. Autoregressive AR models. Okay, so what can we say about this? Well, definition 22. So X follows an AR model of order P if it is stationary and satisfies following relationship, which is that xt is phi1 xt minus 1 plus so on up to some phi p xt minus p plus some epsilon t. And this is, of course, for all t in our z space, and for some phi 1 to phi p reals. And it's very important that phi p is not 0, because then we would be of a previous order. And then the epsilon is white noise. Okay. Okay, so what we've done is essentially to regress X at a given time against its previous P values, right? So there's strong flavor here of regression, right? Linear regression, in fact. Okay, so that we can analyze this further, we need to introduce an operator that is called the Backshift operator. So let be the Backshift operator, i.e. B applied to xt is xt minus 1 for all t in this capital T. And we also have powers, by the way, so we can have BH xt, which is xt minus h, and this is for all t and h in here. Well, actually, h really should be here, natural. Okay, so these are powers, yeah. So then the autoregressive operator is this capital phi, depending on b, which is equal to 1 minus phi 1 b minus so on to phi p b to the p, right? So that what we have in the expression of the AR definition, and let's call it star, so that star is more succinctly, we can write it as this AR operator applied to xt equal to epsilon t, right? And what we've seen is that the xt's which were correlated to their other values have been decorrelated, right? If we look at this expression, right? So this decorrelates X into white noise, yeah? As we can see here. Okay, so let's for a second. What time is it? Okay, we should run, but yeah, let's focus on okay, so we focus on, so to understand the model, so we focus on looking at this star relationship with P equal 1. Okay, so let's begin with this case. So what we have is that we're going to write phi for this phi 1, but without stationarity at first, yeah? What do I mean? Well, I just want to look at this relationship, the star relationship up there, but without assuming stationarity to see what we can get out of it. Yeah. Okay. So, and still in the P equal 1 case. Yeah. So let's first of all assume that this guy is less than 1. Okay. So if we have this, what we get is that the xt, you know, if we try to invert this relationship here, then this is going to be this epsilon t, or you know, also written as this. And you can check, and this is in the notes, so definitely try to understand the reasoning there. This can be written as this, yeah. Okay, so this is in the notes, you should check that, yeah. And so, of course, you know, we've written x in terms of the white noise only with these guys that are absolutely summable, right? And so we have that x is linear. And so in turn, x is stationary. Okay. By similar arguments, so just to recap, what I've said is that if we focus on the P equal 1 case and only look at the defining identity of the AR definition, but without assuming stationarity, we have that if we assume that the parameter is less than 1 in absolute value, then we get stationarity straight away. So we wouldn't have to assume it. Yeah. By the way, so if we have, you know, in this case, we'll be interested in understanding what the autocovariance function is, right? Because we said that we have the mean, but then we are interested in understanding the first order dependencies. So one should compute always this autocovariance function. And in this case, and this I leave it to you to compute it. And you should use the same arguments that are used in notes to show that. Then you will see that it can be written as this, yeah? And so we see a very characteristic property of the autocovariance functions of AR models, and is that the autocovariance decreases as the lag increases. Okay, so we have dependencies that sort of die off with the space between elements in the time series. Okay. What about if, you know, in the other case in which we have this to be greater than 1? Well, so you can check this, and xt cannot be written you know, as above, as in terms of its past and all of its past values. Indeed, it is, well, let me just write maybe on the contrary, well, or indeed, it is explosive, by which I just mean that if you try to write it in terms of the past, you'll see that the expression will eventually explode. Yeah. So if you have this infinitely many terms, and so it's not useful to write it in terms of the past. But what you can do is to write it in terms of the future. Yeah. So you can write it as xt, and then the sum from j equals 0 to infinity of the phi to the minus j now, t minus j, t in this in here. Okay, good. So you can write it in terms of the future. So how is that useful, right, for us? Because of course, in a time series, we'll only observe values, as in we'll wish to predict for the future and not for the past, right? So this model is useless in practice, yeah. Even though one can show that this is stationary, yeah, because this is linear, right? So this is linear and therefore stationary, but it's still useless in practice. So we've seen that so far we didn't need the to assume the stationarity, just the defining identity was enough. And then we have this last case, which is the one that rules out, well, that therefore, well, okay, we'll see what happens here. So if you have, and this is absolute value, of course. So this is the random walk. Okay, so random walk, or phi equal 1 is random walk. We all know that the random walk is not stationary. Okay, you can check this if you haven't seen it. Cannot be stationary. So star rules out, well, or star plus stationarity. Okay, so definition then, excuse me. So definition of AR rules out this case. Okay, so we need the stationarity from the AR model. Okay, so we see that really stationarity is key, right? And so we could be wondering, okay, so in cases in which the order is larger than 1, then how do we know if the identity gives rise to a stationary time series? Well, we have the following result to answer that. So proposition 3. So a stationary solution to star exists if and only if we look at this AR operator, but we look at it as a function of the sorry, not of Z, but of the complex plane, so the complex numbers. Okay, so rather than plugging in B, this capital B, the backshift operator, you plug in the complex numbers. So even only if this guy or X, okay, and this is terminology, or X has no unit roots. So we say sometimes that X has no unit roots. Of course, we mean that the capital Phi has no unit roots. And what do we mean by having no unit roots? Well, it just means that this guy is going to be distinct from 0 for all Z in the complex numbers, such that this guy is 1. Yeah. So there are no roots that have unit modulus, right? And furthermore, if a solution exists, it is unique. Okay, so we've seen now how to get AR processes, basically, from the defining identity. Okay. So we also saw that even when you have a stationary process, in the example of order 1, there is still something that is desirable for modeling purposes, and that is that we can write any value of the time series in terms of the past and not of the future, and that has a name. Okay, so that's called being causal. Okay, Okay, so proposition 4, well, actually, let's define causality first. So definition 23, X RP is said to be causal if it is linear with these guys being 0. Okay, as in if it satisfies the identity of being linear, so if it can be written in terms of this white noise, but only of present or past values of the white noise. Okay, so that's all I'm saying here. And then proposition 4, when do we have causality for ARP models? Well, X ARP is causal if and only if this guy is distinct from 0 for all z's in the complex numbers such that this guy is modulus is less or equal than 1. So there are no roots basically from the from this disk of radius 1. Yeah. Okay, so now we've seen autoregressive models. We've seen how to get how to get them to be stationary, because they are stationary. So how to get them via the identity, the defining identity, and then also how to get causal ones. Yeah. So let's now move on to moving average models. So moving average MA models. Okay, so we have so definition 24, I guess 24. So X follows an MA model of order Q. If we have that, we can write XT as follows. So essentially, we're now writing it only in terms of white noise guys. Okay, and this is, of course, for some theta 1 to theta q guys in the real line. Theta q must be distinct from 0, because otherwise we have lower order. And then epsilon, as usual, is white noise. Yeah. Okay. So, of course, by definition, X, if it comes from this model, is stationary. Yeah, because it's linear straight away. Yeah. And we can define the MA operator just as before, as capital theta of B equal to 1 plus theta 1B plus so on to theta q B to the q, right? So that, and then we can write star star here, so that star star is xt being equal to this guy applied to epsilon t, right? Okay, so again, let's focus on the q equal 1 case. I'm not going to have so much time, but let's try to finish this. So focus on the MA1 example for now, and I'm going to write theta for theta 1. So you could check the following, and is that the autocovariance function of this guy can be written as 1 plus theta squared sigma squared if h is 0. So this is the variance, basically. then the covariance between adjacent points is given by that, and then any other covariances are 0. Yeah. Okay. So rather than having this sort of slowly decaying autocovariance or covariance between more and more distant points, we have that it is exactly 0 from 1 onward, well, from 2 onwards. Yeah. Okay. So, and let me also point out something about this model, and is that it's not identifiable. Okay, at least from the first 2 moments. So this guy is unchanged if I substitute theta by 1 over theta and sigma squared by theta squared sigma squared, right? That should be clear. Which means that, as I was just saying, the model is non-identifiable from, at least from the first 2 moment properties of moments. Yeah. And it is non-identifiable at all if the white noise is Gaussian. Okay, so if we have that, these guys are actually Gaussian. Okay, so this is Gaussian white noise. And this is, of course, because we fully determine the process by the first 2 moments. So if it's not identifiable from the first 2 moments, then therefore it's not identifiable at all. Yeah. Okay, so we need to choose. So this means that we need to choose, in this particular case of Q equal 1, order 1, we need to choose between theta less or equal to 1 and theta greater than or equal to 1, right? So how do we choose? Well, let's note that in the first case, we can write, and this is again for order 1, so we can invert the relationship that we had with the operator, with the MA operator, if and only if this theta is less than 1, okay? i.e., this is what we say, that X is invertible. So invertibility is useful for stats. We'll see for statistical estimation and inference. So we choose this parameter space. Okay. Okay, so let's then generalize this to MAQ processes. So definition 25. So definition 25, we have that X follows an MAQ process is invertible. Right, so this is the property that we wish to keep, to have this lack of identifiability, to avoid, excuse me, the lack of identifiability. So it is so if there exists a sequence of real numbers such that, you know, they're absolutely summable, and we have that epsilon t can be written now in terms of the x's. Yeah. So this is essentially the invertibility that we saw, yeah, before. And now, okay, so that's the definition, but how do we have invertibility? Well, again, we can look at the zeros of the operator, now in this case, the MA operator, and we have that, so proposition 8, X is invertible if and only if this operator doesn't have a zero for all z's in precisely this disk again. Okay. Okay, and so we had this property that the covariance function was 0 from the order, or from 1 plus the order onwards, and so there is a question as to whether that is the case for MA processes, and indeed it is, and it's much stronger than that, because it turns out that any process that has that in the covariance is actually an MA process. Okay, so let me just finish up with that. So definition 26. So X is Q correlated if X is stationary and gamma X H is 0 for all H greater than Q, and gamma X Q is distinct from 0. Okay. And then the proposition that tells us, you know, when this happens. So we have, why do I have 8 before and now 6? Excuse me that I'm moving this somehow. Yeah, that should have been 5, I think. The previous one. 5. So that was 5, excuse me. Now this is proposition 6. Okay, so if X is Q correlated, then it turns out that it cannot be anything else than MA of order Q. Okay. So these are pretty important models, and we're only missing basically ARMA models and ARIMA models, which are very related, and the definitions are actually immediate from what we've seen. But I don't want to go much, any more over the time. So I will just begin the next practical with the definitions, and then we can. So I will include them in the notes. So please take a look at them, just so that you can do the practical. But I will of course cover them at the beginning. Okay, so we're done. If you have any questions, I have a couple of minutes.